An English mathematician once said, "Just because can't find a solution, it doesn't mean that there isn't one." And like any other concept in mathematics, it also applies in real life. Sometimes, finding which is not the right value is the solution to the problem. And that's the concept of inequality. Hi, I am Mary Grace Guevarra, a secondary mathematics teacher. Let me welcome you to another video lesson on mathematics, and I invite you to follow along as we do exercises in this video. Let's begin. Today, you will learn about quadratic inequalities. After you watch this video, you will be able to define and describe quadratic inequalities, give examples of quadratic inequalities, solve quadratic inequalities, write the solution to a given quadratic inequality expressed in interval notation, inequality notation, and in graphing, and solve word or real-life problems applying the concept of solving quadratic inequality. In our previous lessons, we talked about quadratic equations, the different methods of solving, as well as solving word problems that involve the concept of quadratic equations and rational algebraic equations. Today, I'm going to teach you all about quadratic inequalities. Now, let us get started. A quadratic inequality is an inequality that contains a polynomial of degree 2 and can be written in any of the following forms. Ax squared plus bx plus c is greater than 0, ax squared plus bx plus c is greater than or equal to 0, ax squared plus bx plus c is less than 0, and ax squared plus bx plus c is less than or equal to 0, where a, b, and c are real numbers and a is not equal to 0. To solve a quadratic inequality, we will be guided by the following steps. Number 1. Find the solutions or zeros of the corresponding quadratic equation and arrange the zeros in increasing order. The zeros are called its critical numbers, critical points, or critical values. Number 2. Plot these numbers on the number line as open or closed points based upon the original inequality symbol to separate the line into 3 intervals. 3. Choose a test value in each interval to see if the interval satisfies the inequality or not. If the test value produces a true statement, the entire interval will be true. If the interval produces a false statement, the entire interval is false. 4. Clearly graph your solution and state the solution set using interval notation or inequality notation. Let us have this example. Let us solve the quadratic inequality x squared minus x minus 12 is less than or equal to 0. To solve this, it means to find all the values of x that would satisfy this inequality. First, we will solve this by hand, and then we will also show you can solve this graphically. So to solve this, we first want to determine the x values for x squared minus x minus 12 is 0. So we will solve this using factoring method since the left side of the equation is factorable. So we will factor x squared minus x minus 12, and the factors are x minus 4 and x plus 3 equals 0. We set each factor to 0 and then solve for the linear equations. So we have x equals 4 and x equals negative 3. These are called critical values. These two values are when x squared minus x minus 12 is 0, and because the unique inequality symbol is less than or equal to, these two values are part of the solution. But there are many more solutions we need to find. So what we'll do now is we will use these two values, 4 and negative 3, and we'll put this on the number line. Because of less than or equal to the inequality, these two are part of the solution. So if we plot this in the number line, we will use closed point like this. There is how we've now formed 3 intervals on the number line. Interval on the left, then on the middle, and on the right. So for the perspective, we put 0 in the middle. Now let us find the test value in each interval and test to see if it is satisfied the original inequality. If the test value satisfies the inequality, then the entire interval is a part of the solution. If the test value does not satisfy the inequality, the entire interval is not a part of the solution. So, for our test values, we cannot use these critical values, negative 3 and positive 4. So, we will pick one number for each interval. So, we have negative 4 on the left, 0 in the middle, and positive 5 on the right interval. We will now substitute these values in the original inequality, and here's the computation. Notice that if x is negative 4, it produces false statement. If x is 0 in the middle, it produces true statement. If x equals 5, it produces false statement also. So, again as a review, we have true in the middle of the interval, which means that this is the solution, and false on the left side and the right side of the interval. Now, for the solution set, so the solution set can be expressed in two ways, either in interval notation like this, open bracket, negative 3, comma, positive 4, close bracket. We use bracket to express that these 2 points, the negative 3 and the positive 4, are parts of the solution. And we can also express the solution set by the inequality. So we have negative 3 less than or equal to x less than or equal to positive 4. Now, as I mentioned at the beginning of the video, we can actually solve this quadratic inequality very quickly by graphing the function f of x is equal to x squared minus x minus 12, or y is equal to x squared minus x minus 12. So here's the graph of f of x is equal to x squared minus x minus 12, because we want to know when x squared minus x minus 12 is less than or equal to 0. That's going to occur when the function is less than or equal to 0. Remember, function values refer to y values. So, in the y values are less than or equal to 0. Function is on or below the x-axis, which would be this piece of graph here. And notice that this occurs along the x-axis from negative 3 to positive 4. And this interval is the solution to our quadratic inequality. Now, let's move on to our next example. Let us solve the quadratic inequality 2x squared plus 3x minus 5 is greater than 0. First, we will solve the corresponding quadratic equation 2x squared plus 3x minus 5 is equal to 0. Again, the left side of the equation is factorable, and the factors of 2x squared plus 3x minus 5 are 2x plus 5 times x minus 1 equals 0. We set each factor to 0 and solve each equation. Therefore, x equals negative 5 halves and x equals 1. These are called critical values. We plot these critical values on the number line. We pick one number on the left of the interval, one on the middle, and one on the right interval. We use open points in the negative 5 halves and 1 since negative 5 halves and 1 are not part of the solution. We will use negative 3, 0, and 2 in each interval, and we will test these values and solve whether the interval is true or false. For the computation, we have, if we use x equals negative 3, it produces true statement. If we use x equals 0, it produces a false statement. And if we use x equals 2, again, it produces true statement. Therefore, the left and the right side intervals are the solution or the solution set. So, these are now our solution set. We will write this in two forms. In interval notation, we have open parenthesis, negative infinity, comma, to negative 5 over 2, close parenthesis, union of open parenthesis 1, comma, to positive infinity, close parenthesis. We use the parentheses because it tells us that negative 5 halves and positive 1 are not part of the solution. Or we can express the solution set in inequality symbol. We have x is less than negative 5 halves or x is greater than 1. Let us graph 2x squared plus 3x minus 5 is greater than 0. To solve 2x squared plus 3x minus 5 is greater than 0, graphically, graph the function f of x is equal to 2x squared plus 3x minus 5. Or y is equal to 2x squared plus 3x minus 5. So this inequality is going to be greater than 0 when the function is greater than 0
When we talk about function values, we are talking about y values. So the y value has to be greater than 0 when the function is above the x-axis. Notice how the y values are positive here on the right because the function is above the x-axis as well as on the left. When the function is above the x-axis, but we are looking for the solution in terms of x. So on the right, the function is above the x-axis when x is greater than 1. So on the x-axis, it would be an open interval from 1 to infinity, and on the left, it would be open interval from -5/2 to -infinity. We don't include the x-intercept here because we know that when it's greater than 0 and not greater than or equal to 0. There are quadratic inequalities that involve two variables. These inequalities can be written in any of the following forms. Y is greater than ax squared plus bx plus c. Y is greater than or equal to ax squared plus bx plus c. Y is less than ax squared plus bx plus c. Or y is less than or equal to ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Here are some examples. Have you ever asked yourself, how are quadratic inequalities in two variables illustrated in real life? The following is a situation where quadratic inequality in two variables is illustrated. The floor of a conference hall can be covered completely with tiles. Its length is 36 feet longer than its width. The area of the floor is less than 2,040 square feet. And here are guide questions for us to answer or solve this problem properly. Number 1. How would you represent the length and the width of the floor? So the width is represented by x and the length is represented by x plus 36. Next, what mathematical sentence would represent the given situation? The mathematical sentence would be x times x plus 36 is less than 2040, or x squared plus 36x is less than 2040. Now, what are the possible dimensions of the floor? How about the possible areas of the floor? Here are the answers for the width, length, and area. For the width, we have 15 feet. For the length, 51 feet. And for the area, 765 square feet. For the second set, we have width, 22 feet, length, 58 feet, and area, 1,256 square feet. And for the third set, we have 30 feet for the width, 66 feet for the length, and for the area, 1,980 square feet. Now, this is now the question. Would it be realistic for the floor to have an area of 144 square feet? No, it is not realistic to have a conference hall whose width is too narrow. Now, it's your turn. For the evaluation, let us find the solution set of each of the following quadratic inequalities using interval notation or inequalities and then graph on the number line. And for number 10, here's the problem. A company decided to increase the size of the box for the packaging of their canned sardines. The length of the original packaging box was 40 centimeters longer than its width. The height was 12 centimeters, and the volume was at most 4,800 cubic centimeter. Here are your guide questions for you to answer this correctly and with accuracy. Please feel free to go back to the previous discussion to review our lesson. And to check your solutions and answers,
I hope you enjoyed this lesson. This is Ma'am Mary Grace B. Guevarra, and join me again next time as we make math easy. God bless us all.